Brian, your president. So we're going to start off with the beginner session. So find yourself a seat, and I'll talk a little bit more later.
Hopefully this thing doesn't everybody's
Could this be a long talk? 98% of it's hydrogen. Everything else is junk.
Everybody hear me okay?
No,
you guys can't hear me.
Getting in the hang of being a church.
Just before we get started, a quick show of
As
hands.
time goes on, I'll tell you what all the other
How many
little jobs.
people do we have here that have joined the club in the last, say, 6 months? Quick show of hands.
I think that's
Sorry, was there 5?
yeah.
Okay. I'll be talking after this presentation about something that might be of interest to you, and then Brian will be carrying on, but that's good to know. Welcome, by the way. Well, for those of you that don't know me, I'm Darren Hennig. I'm actually on the Executive Council now, and I'm doing all of the beginner sessions, so thanks for coming out tonight. It's nice to see the weather starting to kind of warm up, so hopefully in the next couple of weeks we'll have, I guess, depending on whether Jay was right on his email there, we might end up with some challenges in Dundee this year. Tonight's talk I thought would be kind of interesting. It's going to be basically a historical journey. I'm just going to do kind of the broad brushstrokes on this one. Being a physical chemist and an analytical chemist, I always think chemistry is very interesting anyway. So I thought this would be kind of a nice way, especially for some of our new members, to kind of understand there's probably been a similar talk like this maybe many years ago. But just looking at the journey that we've kind of done over the last 2,500, 2,600 years to get to where we are kind of now and moving forward. So don't worry, I won't have any complicated formulas or anything like that. So for those of you that didn't like chemistry in high school or in college for any reason, you don't have to worry about having complicated equations and no big math either. So you won't have to worry about either. So everybody's going, okay, good. So if you think about it, I know astrophysicists and physicists in general always say everything is really technically physics, and they are right somewhat, but really chemists and physicists look at really the same things, but physicists tend to emphasize on forces and energy mostly, whereas chemists obviously deal more on the material side of things, the matter. So when we look at least from an astronomical perspective, we have things like stellar evolution, coupled with physics, of course. Planets and atmospheres and how they evolve, and also biological processes like here on Earth as an example, does have a huge impact on the way the planet has developed over the millennia, or eons, I guess I should really say. Of course, comets and asteroids as well, when we look at them as being sources for maybe the building blocks of life in early solar system history and so on. We learn a lot looking at the chemistry of these things and the actual material breakdown of these. And to a limited extent, even though it technically falls under physics to a large extent, even nuclear transmutations sometimes can fall under, I guess we'd call it nuclear chemistry as kind of a blanket. And there's a lot of other things in the universe that chemistry is involved with, but these are the core ones as we're dealing with, at least from an astronomical perspective. So we're going to look back into time, and as I say, we're going to do broad brushstrokes on this one. Because there's a lot of steps, and I'm going to just sort of do a little breadcrumb all the way through, and I think you'll see where we're going with this as we move forward. So, first of all, we're going to start out in the 5th century BC. Anaxagoras, he was a Greek philosopher, and he was born and obviously lived before Socrates. He had a couple of different contributions, obviously, to astronomy, but the main one that I want to really emphasize, I'll leave that up for a minute for people to look at. Two things. First of all, talking about materials being made of imperishable substances. And he thought the stars were very hot, metallic, or stone-like orbs, and that they were very far away. And the reason that we couldn't see them as being brighter and feel the heat off them was because of that distance. So it's kind of interesting. Here we are, 5th century BCE, and he's not really that far off from what we know now. We'll get back to that later. So really the big takeaway here is the sun is very hot, and the stars are too far away to light and heat the Earth at night, at least from the perspective of this talk today. Then we go a century later, and we have Aristotle, and of course he's known for a wide range of contributions, and he studied many different disciplines, including ethics, logic, and so on. He surmised that the sun size is larger than the Earth using geometric calculations, and of course looking at the shadows cast from the sun, and he was right, although of course we know a lot more now than we did back then. He also thought the stars were too far away and made of a different matter than on Earth, and it had to do with the motion in the heavens, is how he came to this conclusion, because everything falls vertically, but here the stars are out in the heavens are moving in sort of arcs. We know now that's because of the Earth's rotation, but back then they were still developing their concepts. So, and then also the concept of the ether as well was another major contribution here, and that sort of pervaded for many, many centuries later. And of course, because the stars are so far away, they're basically unchanging. So the big one here that we take away is that the stars are very far away and the heavens do not change. Basically, the heavens are immutable. Okay. So even though those concepts and a lot of the Greek philosophy pertaining to the nature of the universe we know now to be different than what it was originally, the thing is that it really survived. Fragments of this went all the way almost to the 19th century in some cases, even as science was developing and disproving some of this. So it wasn't really until advancements like physics and optics and even astronomy and astrometry actually too, were able to truly unravel the mysteries of the universe. So we're going to actually jump ahead 1,500 years approximately from the time of, even though there were contributions, I only have a half an hour to do a talk, so we can only go so quickly, but here's where the relevant stuff starts to really deviate and kind of get the ball rolling. So we looked at, now throughout history there's been recorded examples of new stars in the heavens or things that people couldn't explain. And one of the main ones was at 1054. We know the remnant now to be Messier 1 or the Crab Nebula, but in 1054 this was a supernova. And it was well documented by Chinese astronomers, and eventually once sharing of information happened post Marco Polo, you know, some of this information ended up making its way into Central Europe as well. But the big one here is in 1572 when Tycho Brahe was doing his observations, and he witnessed a supernova. He wrote his treatise called De Nova Stella, meaning of new stars. And this is the first time that somebody was really starting to kind of put this together and go, maybe the universe isn't really static after all. We're starting to see changes here. There are other examples, but these are some pivotal ones. Okay, so this is starting to really generate some interest, and of course, coupled with people like Galileo and Kepler and so on, we're starting to see a huge surge in knowledge acquisition and changes in the world view, if you will, or how the universe works. One interesting thing with Galileo, and I know Jerry did a very interesting talk a couple of months ago, and I hope he does the rest of it soon, because that was very interesting, some of that political intrigue. I'm going to kind of stick to what we call the normal historical parts for now, okay? So I apologize if you can correct me later if you'd like. But anyway, in 1610, of course, he was observing Jupiter, and during the early parts of the, I guess, 17th century, when he was doing some of his observations, even closer to home he was seeing changes, because the moons that now bear his name, the Galilean moons, every day you'd see them in different positions. So even closer to home, we're seeing the heavens not being immutable. So this is really starting to paint a little picture here for the burgeoning scientific community of the day, that maybe Aristotle wasn't so right after all. And of course, there was other reasons for this as well, and of course with Copernican theory and so on, just a huge revolution in looking at things. So another thing that Galileo did is he showed by simple measurements of parallax, along with some of Brahe's observations as well, that the stars, distant suns, are much further away than previously thought. So this is going to have some impact later on. But basically, the observable universe is definitely not static, and that the stars are much further away. That's really the big takeaway here. Now, optics was essential to investigating the heavens, because we were seeing them with our eyes, and I talked a couple of months ago about, or actually it was the last month, no, it was the month before, on how our eyes work and so on. And so really, even though there was a lot of contributions, including from Arab and other Muslim scholars that developed some of the mathematics and theories for optics, really where we start to see things take off a lot is right around 1704, about a century later, with Sir Isaac Newton. And of course, he's known for all sorts of contributions, but what's relevant here is his book on optics here. It was a major work on light. He came up with a corpuscular theory proposed, and his investigations, especially the prisms, he discovered that white light is being broken up into a spectrum, and he coined the term spectrum, I believe. I could be wrong, somebody can correct me later if they'd like. But this is sort of where we're starting to see white light now that we're looking at, both from the heavens and in our surroundings. It's comprised of colors, and that this will become very, very important as we move forward. So Thomas Young, physician and polymath, during the time that Newton had proposed corpuscular theory, there was a lot of suggested evidence that it's possible that light has really a wave-like nature more than particles. So one way to prove this is that Thomas Young came up with a very simple experiment, and he found that light wasn't behaving like particles. He was starting to see wave-like interference. And of course, basically the premise of this particular experiment is so on. Like if light was strictly particles, then you would see a pattern observed on the screen here coming from both of these, where you would get a contribution and it would form a normal type of shadow where you have the umbra and penumbra crossing. When he did it with a single slit, of course, this is what he saw on both sides. But as soon as he ended up putting both slits in and illuminating them using sunlight, wave theory would predict this, particle theory would predict an overlap like down here, and what he saw was what was showing up on wave, basically a diffraction pattern. So therefore that was proof that light actually is behaving like a wave. So because light has a wave nature, of course, this will become very prominent later on as we start to investigate the heavens. So we're starting to see a lot of changes here. Again, kind of a resurgence of things. Moving forward a few years, William Hyde Wollaston, an English chemist, besides discovering a couple of the rarer precious metals, he was one of the first to use a slit to study the solar spectrum. And what he was finding is that you're getting a series of these dark lines. I don't know if you guys in the back can see it very easily, but there's these really dark lines in here in the spectrum. And we know them now to be Fraunhofer lines, and I'm actually going to move forward. But before I do that and talk about Fraunhofer, I was going to say, so what we're seeing here is the spectrum is not continuous. What are these dark lines? They weren't sure if they're just natural separations or what. So we're starting to get some weird things going on now that we're investigating in the solar light coming off the sun. So moving forward about 10 years, of course, Joseph Fraunhofer, he's known for many things. He's known as the, whoops, I went too far there, sorry. He's the inventor of the spectroscope. He was actually developed it to study special properties of glasses like refractive index and so on. And when he turned his spectroscope to the solar spectrum, he was finding a bunch of more lines than even Wollaston saw. And he started to catalog these because he could use these waves. This was sort of a rudimentary way of using solar wavelengths to act as wavelength standards, basically. We can now use lasers, but in those days they couldn't. So this was a way for him to be able to do this. And he didn't necessarily associate these at the time, but we know them now to be associated with some of the, like as an example, you've got hydrogen alpha C line, okay, and so this is in the red region of the spectrum, and this is the blue region, even though it's monochromatic. It was a monochromatic photograph that we found. So the solar spectrum now has many more lines than was originally thought, and at specific wavelengths, suggesting now we might have a celestial particle going on. Well, Fraunhofer maybe didn't fully understand it. I think he was a pretty smart fellow, and this was really starting to imply that we might actually have some information encoded in the light coming from the sun. We might be able to use it for something. Now, just a sidebar here, I'm just using Comte as an example, but there were many philosophers in the day as some of these discoveries were happening. It was throwing the world upside down. I mean, people were talking about existentialism and the nature of man and the universe, just from a philosophical standpoint. And one of the big things that he suggested here was that in his treatise of discussing scientific topics in general, is that the stars are too far away and they may be beyond our grasp unless we can actually get out there to see them. So it started to sort of divide the scientific community a bit. Maybe these guys are right. Maybe we're not able to know everything that we can know because we can't get there. They're too far away. And then the other mode of thought is, well, no, we're starting to find stuff out. Maybe there is a way to. So it's kind of interesting how this sort of affected scientific thinking in the mid-19th century a little bit. So his basic suggestion was the stars are beyond, are they maybe beyond our reach to fully understand? Well, then we scroll forward about 15 more years, and now we have Bunsen and Kirchhoff, two famous German chemists. And they developed, obviously Bunsen developed the Bunsen burner that you guys all used in high school chemistry and so on. They were studying the spectra of gases, both heat gases and cool gases illuminated by a source. And they discovered atomic spectra. And in fact, they were able to identify, when they used actual elements, fingerprints for these elements. So if you had, let's say, a hot rod of iron, say as an example, and it's glowing, and you put it through either a prism or a diffraction grating the light through here, you get a continuous spectrum. Okay? Now if I take a hot gas like hydrogen and pass it through, so the gas is hot and glowing, or it's ionized, or it's in a flame where you're burning it, now you're seeing this emission spectrum here. And then if the gas is cold and I'm illuminating it now instead with the source, now we're seeing absorption lines here. And so the thing is here that's very interesting is there's a correlation. So it's really suggesting now that there might be a fingerprint for the elements, and this started to lead towards speculation that we might be able to use it for astronomical purposes as well. If there's gas out in the universe, we should be able to take distant light coming through that gas and see what it's made of. So just a quick sidebar before I get onto that. I just wanted to mention about these dispersive elements just very briefly. The transmission grating that's here, basically what happens is you have light coming through, and what a transmission grating actually is, imagine almost like a grill on the front of a car, right? You have a clear optical surface, and it's basically like a double slit mat. You've got parallel lines and grooves all the way through, very, very finely divided. And of course, when you pass light through it, you actually get diffraction, just like the double slit diffraction, but much more complex. And there's some math on it, and I promised I wouldn't do math today, so I'm going to leave it alone. But you have this zero order, which is basically the undeviated line, and then you have two orders here. And you'll notice that instead of a prism where the red doesn't disperse very much, but the blue bends quite a bit, it's the opposite in a grating. Now at this time, they were starting to develop better techniques to deal with and machine surfaces on glass, although it's still a while before the grating became the norm. However, I just wanted to mention this because in modern day, we actually quite often will use these reflective gratings now with mirrored surfaces, and so they actually put the striations on a mirrored surface. That's quite common in astronomical investigations currently. Okay, so we switch forward to 1862, and we have William and his wife Margaret Higgins, and they were one of the first to put a spectroscope on their telescope and start to actually record spectra. And he was interested in looking at some of the mission nebulae. What we know as a mission nebula today, these bright nebulae, and as an example, he was looking at the Orion Nebula, and he saw hydrogen in there. And it seemed like everywhere he was looking, hydrogen was present, because you could identify it from the emission lines, or in some cases absorption lines, if they were cooler spectrum. This led to the discovery that hydrogen might be a predominant element in the universe. So all of a sudden now, we're starting to see hints that, okay, our sun has hydrogen. The other stars are looking, and other things are looking to have hydrogen as well. What does this mean? So his spectroscope here on the back end of the telescope, of course, is what he was using to do these investigations. Now jump 2 years forward, and now what you have here is, this is the Cat's Eye Nebula in Grating, and this was one example historically where he found these, when he was starting to investigate here, he found that there was two new lines that didn't correspond to any element. So, at least on Earth, that was known. And so he coined this new element, possibly nebulian. Of course, that was a suggestion. We now know it to be double ionized oxygen, or oxygen-3. And of course, many of you more seasoned observers will have oxygen-3 filters that you'll either use visually or photographically to help break these out. But at the time, this was something new. And again, it's suggesting that maybe the heavens are accessible after all. Okay. So then we scroll forward another few years, and Jules Janssen, of course, was interested in looking at solar sites, particularly the corona and the prominences that were present and were already recorded in earlier eclipses. He wanted to use this as a way to see what's going on with the sun. So he took the spectra of the gaseous corona, and it was one of the first times that he got decent data on this, and he developed the coronagraph so he could do this without having to wait around for the next solar eclipse, total solar eclipse. And the spectra showed bright prominent yellow line at around 588 nanometers. And again, this is a new element. People are going, what's going on here? There's something new again that we don't see on Earth. So it's again suggesting that we may have definitely touched upon being able to have technology to be able to really truly access the stars. We're seeing it on the sun. We're seeing it in distant nebulae. What's going on? This is exciting stuff. So just where the helium line is, just to show you here, when we take a spectrum of the chromosphere here as an example, this wasn't his data, this is just an example. Right near it is the sodium doublet, what we call the sodium D lines, and then right next to it is the helium line. So if you use enough of a resolution in the spectrum, you can actually discern that very, very readily from that spectrum. But again, it didn't correspond to anything that we knew of at the time on Earth. And his counterpart in England, to be the founding editor of the scientific journal Nature, which is still present today, Ludwig Jansen, he was studying this new line, and he coined the term helium for the element. And it wasn't until a little over a quarter of a century later that we actually found helium on Earth. So it was named after Helios, which is the Greek name for sun. And again, this is the actual spectrum of helium. You can see the very prominent yellow line. Okay. So again, exciting stuff, right? We're using simple equipment, but boy, we're starting to get an idea of what the sun's made of here. Here we've got a solar spectrum, and look at all these elements in here. I mean, this is by no means fully comprehensive, but you've got oxygen, sodium, mercury, magnesium, iron, calcium, hydrogen, obviously, helium, titanium, nickel. I mean, these things are showing up all over the place. So now we're starting to understand the elemental breakdown of stars. This is starting to allude to what potentially could be the chemistry of stars. That's why I gave the talk. So now we're forward just a little bit further, and now everybody's starting to come on board with using these spectroscopic techniques now. And Pickering, who was the head of the Harvard College, was getting huge volumes coming at him of spectroscopy data, and it was becoming overloaded. So he hired his housekeeper, who was a former school teacher, to actually start cataloging these, and she ended up assembling an all-female team. And so the guys would go and generate the data, and then they would go and sort and collate and get it all put together, all manually. That probably was some pretty interesting work in the day. But even herself, she did over 10,000 plus spectra on her own. At this time, they were also seeing spectral classes starting to show up. So we're starting to see now certain stars having similar characteristics based on their spectrum. And during her investigation, she also found that there was some spectra that didn't correspond when they were looking at certain white stars. Didn't correspond to what they were seeing in some of the other stellar populations. So she was one of the first to. She was the first person to discover white dwarf stars. So pretty cool, eh? All from using the spectra. And we move forward a few years, of course, along with the rest of the female team. Annie Jump Cannon, who was one of Pickering's women, they called them, began to classify the stars by spectral and temperature types. And of course, she came up with the classification scheme that we have today. And of course, it's had some modifications to it, but it basically was the foundation. They were using the Bomber series lines in the spectra in order to do that. I'll talk about that in a minute. But it's amazing. She did almost 500,000 spectra herself in her lifetime. Still holds the record. That's amazing, I think. True testament to her dedication. Anyway, when we're talking about Bomber lines, they're basically the hydrogen lines in the visible spectrum. That's called the Bomber series. And what we see is when you have higher temperature of stars, you have atoms that are ionized, so you don't start seeing as many of the neutral atoms that we see. As we get to colder temperatures, we get associations of molecules like titanium oxide and so on. And they show up usually in the middle part of the spectrum here, and also in the red. And it makes the spectrum much more complicated when you have these heavy absorption lines in the spectrum, okay? Because as things get hotter, they're no longer absorbing, right? They're fully ionized and they're transparent at those wavelengths. So again, this is just sort of the classification with some general information here. And if you look at the molecules of H alpha, H beta, H gamma, H delta, and so on all the way up. So it's these lines here that we're talking about throughout all these different spectra. And of of course, on the temperature side, they can use like the Wien relationship, or even later, of course, Boltzmann's relationship to, or Planck's relationship, to be able to actually work out the black body curves, and it can tell the temperature of the star. So they can tell by the shape as well. Pretty neat stuff. So by the end of the 19th century, we had really spectroscopy as the essential tool for stellar investigations, as well as looking at galaxies and so on was starting to come about. And stellar spectra revealed that all stars have similar sets of elements. Granted, I was saying that depending on the temperature, you're going to get a different breakdown, but the star stuff seems to be fairly consistent throughout the universe, especially with the predominance of hydrogen and helium, as mentioned earlier. Stars, of course, with the temperature, they're speculating that there were hot balls of gas. We're starting to see a spectral grouping of similar stars, so now it's alluding to families of stars of similar evolutionary pathways. And so this obviously led into later Russell and Hertzsprung creating their diagram in the 1920s. So we look at nearly 25 centuries going from ancient Greece to just after Pickering's time. We've almost come full circle. As I mentioned before, Anaxagoras ended up mentioning the stars were hot. They were speculated that they were hot balls of metal or stone, and in some ways that he wasn't too far off. And if you really think about metallic hydrogen in the core, it might be stone-like. I mean, it's kind of amazing when you think of the insight there. They had no way of proving it, but it's kind of, I just find that really fascinating. Anyway, and we also know that they were very far away as well. So now we can use this new new for the time, technology to be able to really fingerprint stars and really from here on Earth be able to decode the chemistry of not only stars, galaxies, quasars, all sorts of things now, right? I mean, it's really amazing. So these two things were basically covered there. So really stellar chemistry is, for the most part now here in the 21st century, really been decoded. Now, there were a lot of contributions since the end of the 19th century. Obviously, the Hertzsprung-Russell diagram and there's modifications to this. This is a simplified version. We have different classes like L and R and so on, the cooler stars. But basically, by being able to take the temperature and the brightness with the spectral characteristics, I mean, they can, we're starting to see a really good picture of how stellar evolution happens. Also, we're still learning a lot about solar dynamics, looking at different wavelengths now, like X-rays and in the X-ray regime or extreme ultraviolet. And in the early 20th century, of course, several scientists, including Eddington, he was the first to propose that there's element synthesis going on in the core, possibly, that there's fusion in the sun. At that time, they hadn't quite detected the neutron yet, so it was really the advent of quantum physics and going into the almost really the atomic era before we found out he was right. And of course, moving forward, we learned a lot along the way. So really going into the third millennium, we still have a ways to go, but we really started to decode this very well. And when you start looking at, I kind of like that slide. Just let me throw it out there. So when we look at now supernovae, I guess, and Michelle might be able to elaborate on this more on a talk sometime, is with the gamma ray spectroscopy and high energy spectroscopy, now they can start to see gamma signatures with elements that are forming in these supernovae. So it's pretty exciting stuff because we've actually been able to decode some rudimentary chemistry of the stars very easily. Now before I wind it up, I just wanted to mention for those of you that think spectroscopy is cool after this, maybe I didn't make it quite as exciting as I could have. But you can actually get, there's other pieces of equipment too, but if you want something very easy to do your own kind of spectroscopic investigations, and this is a primer to a talk I'll do later on amateur spectroscopy, but I just thought I'd mention it now because it's relevant. You can get an actual little filter cell that you can either thread onto a DSLR or put on the nose piece of say a CCD or a CMOS camera in a scope, and you can take the light from the scope and it'll actually, on the surface, record the spectra for you. And then you can get software that's very easy to use that can actually give you the spectrum, and you can do your own investigations if you want. Here's an example of using a star analyzer and a refractor, and you can see, I went too far again, I keep doing that, sorry. You can see the zero order image here, which is basically, this is the Ring Nebula, by the way, in Lyra, and there's the oxygen 3 image, and here's the H alpha image. So you can see that you've actually got the spectrum spread out quite a bit. The other nice thing in this case, it's called slitless spectroscopy in this case, because you're not utilizing a slit ahead of the, I'll get into more of that in another talk, but what's really interesting here is you can also study all of these stellar spectra as well as this one here. So it's really interesting to get a wealth of information from one image. So if you take a nice photo in the sky, you not only have a beautiful picture, but now you can do some citizen science with it too, potentially. So I just thought I'd mention that. That's kind of just to whet your appetite for another talk. In the meantime, though, again, through spectroscopy, we've really seen with a lot of these, the spectra of all the elements, we've actually truly been able to unravel the chemistry of the universe. And we're still learning, but it's getting closer and closer and coming into focus. Thank you very much. Now, just before I pass it on to Brian, I have a club announcement here. I'm just going to try and see if I can grab this thing here. There we go. And this should kick on anyway. Got it? Okay, perfect. So as you know, I'm a member of the council. I'm one of the councillors for our RASC Winnipeg Executive Committee. And we were discussing during the, Brian's going to talk more about what was discussed in the meeting and the direction we're going. But in the meantime, I came up with, because I'm doing a lot of the beginner talks, and I've talked to a few people in the audience who come to approach me during the break and so on, or maybe when we go for beer and pizza and so on. And I think it might be high time to do something like this again. I don't know if it was done in the past at some point, but we want to formalize it a little bit more, because I think it'll give, especially the newer members who are just starting out in the hobby, to really get a good start here. So basically the idea here is again, to help new club members to get kind of the right start and kind of fast track, so that this way they're not sitting there spinning their wheels. We're only doing monthly meetings, and of course, depending on the weather conditions, that could be a lot of time to be able to look under the stars. If you can take advantage of some of that time with somebody kind of guiding you along and showing you the ropes a little bit, you can kind of fast track a little bit more and get maximum utility out of your equipment. Also, assistance with maybe even choosing a telescope. If you don't have one and you're looking, we can help you do that as well. We'll also have learning modules for various aspects of amateur astronomy. This is just some examples here. So, how do you just go? Again, this is going to be more formalized, but these are some examples here of what we're talking about. And of course, for those of you that want to do astrophotography, wide-field DSLR techniques and plan focus, either with a DSLR or a CCD. So I'll just let you take a quick look at that, but you get the gist of it. So for those new members that would like to take advantage of it, make sure that you get a hold of either myself, Brian, or Bill. For now, we're the three that have kind of spearheaded this. I started it, and Brian obviously gave his generous endorsement. Bill Crosney, I don't think Bill's here today, is he? I didn't see him, so I think he's still away on holidays. But anyway, we would certainly appreciate some volunteers. So those of you that maybe have a little bit of spare time to assist, we just make sure you let either Brian or me know, and we'll put you on the list to be able to help some of our newer members get started. Now, ideally, because we haven't had this maybe in a while, because I did mention this to Brendan a while back, and he didn't recall, at least in the last 2 or 3 years that we've done this, I was going to say, if anybody feels they need some help, even if they've been a member for two years there or something, or even 2.5, no problem. We're more than happy to help. That's what we're here for. We want to make sure that you guys get the best start and the best enjoyment out of the hobby. Okay, so just thought I'd do that as a primer. There's more to come on this, but we want to definitely be on track for when the weather starts to work out, so you guys can start getting some fun under the stars. Thanks, guys. And how's Mr. Brian here? You're welcome.
Checklist for mentoring spruce wood stuff.
Well, that would make it a little more practical.
People learn something and let's see. It'll be these three times. These three times.
Hey, we're up and running, great. My name is Brian, I'm the president of the club now for the So this is what we have lined up for tonight. Do we, I think Darren mentioned it, but do we have any new members here?
About 5 or 6.
5 or 6, okay,
Come
great.
see us at the rate, please, yeah. Sorry.
Yeah, we'll mention more about it later. Okay, so we have Derek with the beginner session. We have What's Up with Jay Anderson, and of course we have What's New with Michelle. And then of course we have Richard. We're using Star Tools. Richard's here? Great, okay, perfect, thank you. All right. Okay, so I got confirmation. Oh, I didn't change this. Okay, that's my fault. I got confirmation from Danielle. The open house is at 7 p.m. on March the 27th. The topic was supposed to be mission failure, but I thought I changed it, but maybe I just grabbed the wrong slide.
Failure?
Yeah, space mission failure, or something like that. So we'll see what's about. I got this cloud, so I get the 2 files in sync or something like that when I went to change it. So hopefully I grab it before. So anyways, okay, so that'll be interesting to see. Of course, we have the Old Comic Marsh on March the 21st. Of course, Jerry's got something. Jerry's always interesting to see or to listen to. Jerry, I said you, right? Yep. So that'll be interesting. Auroras, it's your topic. So anyways, if you're a member, right, and you do bring a telescope, the fee gets waived, so you don't have to pay. It's a nice outing. I like it. It's really good topics, and of course a chance to get out there on the rooftop and do some astronomy. So anyways, moving on, we have the telescope loan. Now Abdul is taking over from Stan. And so if you have any questions about loaning a telescope, he's got the list. Of course, you will need some ID, and I think we have to fill out a form, but we have quite a selection of telescopes to lend out to members. So if you're not too sure about your telescope or what to buy, or like one of the, it's really nice to have was the PSC to borrow that one and do some solar telescopes observing, which is interesting because you get to see the prominence in real time. Moving on, of course, we have the Manatee Observatory. I'm the director of it. And we're going to, hopefully, this year, develop the flag. Hopefully the flag won't interfere too much. It's open to all members. If you want the key, you can see me. There's a $10 deposit for it. Also, I'll bring a map here, but we have more telescope than what's listed here. We have the 12-inch Meade LX200. We have the 6-inch Dob there, and we also have the 14-inch Dob. Again, I'll show you how to use this because I add this line right here, training at the observatory. I will provide training to use the LX200 and the dome. What else? All right, well, members night, I'm going to cancel that for tomorrow because of the weather. Looks like it's going to be cloudy and there's a possibility of a storm brewing. The roads, I'm not recommending anyone heading out there. I tried it myself. Oh my God, I grabbed the wrong slide. Oh my God. Sorry, I had pictures. Again, it's my fault. Okay, my cloud didn't sync with my files. Okay, I had a picture of me doing the Dukes of Hazzard over some of the snowdrifts. So, and there was a panoramic view of how bad it is out there. So anyways, it was quite, I'm not going to do that again. Because I swear to God, I think I bottomed out my SUV a couple of times. Then halfway through, I stopped and walked the rest of the way. So anyways, I had some more pictures about the warm room. It's fully functional. We have a computer, we have a coffee maker. I was going to show you more about that. But apparently I grabbed the wrong slide, and I'm still learning how to use my Microsoft Cloud. I don't know why it didn't sync. Anyways, but we're definitely going to start out real soon. Like I said, I'm going to get the clearance. Tracy, who's the director at the Manatee Research Facility, to go ahead and plow the snow, but it won't be until next week. It's after the storm. If it's going to snow some more, then I'm going to wait. She does maintain it as best she can, she said, but When I was out there, no. But she did a really good job. Okay, so we have Explore the Universe. Dennis over there does it. It's an interesting program. You kind of get more familiar about the deep sky objects that's out there and how they look. But one of the things that you do is sketching. And you don't have to be, it doesn't have to, it's your personal edification. It doesn't have to be perfect, it's you, right? It's about you learning more about the nighttime sky. So if you go through the program, you get a certificate in the end. Of course, if you want to learn more about it, Dennis is over there. He'd be happy to give you some instructions there. And I didn't have that slide, so I was going to talk more about the mentor program that Darren had. During the break, once you come see us, we'll talk more about it. I'm supposed to list the 6 things that we talked about last night. I swear to God, I made a slide for it, so I don't know what happened there. So we have confirmed 6 programs. And so some of it's great for beginners if you want to learn how to use a telescope or do astrophotography with your DSLR camera. I'll be happy to show you. And if Glenlee doesn't work out because of the flood, we can always go somewhere else. It doesn't have to be at Glenlee. It could be in other areas. I think one of the things, it could be one-on-one or it could be a group. Again, we'll work out the details later. Okay. And I did spell your name right, Darren. All right. So before I wrap it up, this is the council. If you want to talk to us again at the break, feel free. We're here to help you guys out. So if you have any questions about Glenlee, if you want the key, or the programs, or anything about related to astronomy, please come see us. But before I go, Dennis is going to mention something about today.
Can everybody hear me?
You want the mic?
Yeah. There you go. I don't need the mic. I don't want to hear nothing. I've just called up my slide from the cloud. Mine's worked. No? First off, what I'd like to do today is also recognize that it's International Women's Day. So I think that's very important. If you weren't aware, yes, please clap. To bring the point home, astronomy is a science, and it's part of the STEM, which is important, certainly nationally, to our country. STEM stands for, I'm going to mess it up, I'm sure, science, technology, engineering, mathematics. Of course, the last presentation kind of brought all of those sciences together a little bit. And just to recognize some of that, for instance, Judy, could you stand up for a minute? Because there's a scientist up there. Okay, I'm just going to try and point a few people up.
Yeah.
There are other scientists. We're doing lots of clapping, so just hold it for a minute. So there was Judy. Are there any other scientists in the room? Because I know sometimes we get true professional scientists. Somebody, please stand up. Thank you. Just as importantly, Michelle is one of our presenters on a regular basis. Very, very important. She's an active member of our club. Andrea. Stand up, Andrea, up there. Back. Way in the back. Andrea is a science teacher, right? Yes? Good thumbs up there. She's also a past president of one of our club. Very active member as well in a lot of different areas. Gail. Gail, stand up. Another one of our past presidents. She's one of the people that also does a lot of presentations, public presentations, bring in the history into it, all the different night sky objects, how to do it all together. Let's see, Sylvia, I don't think she's here, but Sylvia has been running the Spruce Wood Star Party for a great many years now, so it's another person. The cloud's getting harder to see. We mentioned Karen, stand up. Please stand up. Karen is a member of your council. And now, one last thing. I would like every woman in the room to please stand up. I have a reason for this. Please stand up. Every one of you. I hope every one of you realize you are a role model for everyone in the science, technology, mathematics fields of our industry, and in particular, astronomy. Tonight, there's about 20% when we look at the ratio here. I would really love it if you spread the word and we get it up to 50% participation in our club organization. Thank you very much.
Excellent.
All right. Next, we're going to start out with Jay. What's up? Not sure we should be doing this. The weather certainly hasn't been cooperating very much. I wanted to start off with talk about the weather because I sent a message out 4 days ago saying how the models are giving us 40 centimeters of snow in the next week. Well, this morning one of the models said, nah, looks more like 6. And so I just checked now, and the second model has come around and it agrees that it's going to be 6 as well. And that's made up of some snow tomorrow and snow later on in the week. So all the forecasts that you've been hearing on CBC and the one you got from me currently look like they're going to fizzle right out. And I know you're all greatly disappointed by it. Unable to go and shovel 40 centimeters of snow that the city will then pile up in front of your back lane. So what have we got coming up for March and April in the skies? Well, we have a sunspot. It formed 2 days ago. And it's a little tiny guy. Doesn't have a lot going for it, but it's got its number, 2,700 and something. But this morning it kicked off a little bit of a flare. And when the last check I did on it, they weren't quite sure whether this flare was going to send a bunch of material toward us or whether we would be off to one side from it. But because the sunspot's in the middle of the disk, it usually means the flare is going to fire stuff straight toward us. And of course, we're almost at the equinox where the sun and the earth are pretty much in alignment along the orbital planes. Here's an X-ray image of the sun about the time it was flaring, so it's a pretty small flare. Anyway, what happens if you get a flare? Well, you got a chance for some aurora if that happens. And in spite of Brian's comment about it being cloudy tomorrow night, it looks like you might find about 40% clearing after about 1 o'clock in the morning if you're really interested in looking for aurora. Usually it's better to go to space weather and look it up and see whether anything is active. So here we are, 9:30 in the evening, what the sky looks like, although I've greatly enhanced the Milky Way on it, made it visible. And this is the winter side of the Milky Way, so it's not as bright as the summer one, although it's got some very nice objects in it up here in the more northerly reaches, especially in Oregon here, where we have lots of clusters, and if you can get a good view down toward the horizon, you start to see some of the nebula. Of course, we have the constellation Orion here, with right here is the Orion Nebula, which is a picture that Brian has on his opening screen. And this being 9:30 in the evening, of course, the sky is moving across this way as the Earth turns. And so we see Leo here, which last month was down closer to the horizon at this time. So it's now moved up higher in the sky. And we have the constellation Virgo coming up. And these are important because this area here at the tail end of Leo and in this bowl of Virgo here is an area that are full of galaxies. And you can't really do much with galaxies without a telescope, but the stuff we have out in Glenley is certainly capable of showing it. And in fact, there are so many galaxies in this area that
you almost have to do nothing more than point the telescope in that part of the sky and start pushing it around, and you'll come up across them, sometimes 2 or 3 or 4 or more, all in one view in the eyepiece. Telling which ones they are is a little more difficult, but we have a challenge for you in that this month as well. Up here in this map we have the ecliptic. Well, that's the path of the sun across the sky, or more accurately, this is the orbital plane of the Earth. And we can see we have 2 planets in here. Mars is the only one that's really prominent enough to see. Mercury is sinking down into the sun. No, it's gone into the sun. And so you probably will not see very much, because although this depiction shows that it's fairly bright when you get around 7:30, just after dark, when these planets will be a little higher in the sky is now getting so bright in the evening that unless you have binoculars or telescope, you're only going to be able to see Mars. Mars is in retrograde right now. I'll talk about that in a minute, because it makes some difference. Just to see how things happen, we move ahead until morning, until tomorrow. And you'll notice I've gone to 10:30 because we have a change in the daylight time in the interval. So this is the same time of night, and you notice the little jump of the Milky Way moving along. Now we see the Virgo is higher up, and Leo is getting close to being due south here at that time. And so these are very, very common. These constellations are truly the midwinter constellations. They're the cold weather constellations. And so if you want to go looking at galaxies, you haven't got a lot of choice but to dress warmly and be cold, which is why we have a warm room in Glenwood. And you get up into the more northerly parts of the Milky Way here. We have the California Nebula here, which is very easy to photograph with a camera on a tripod. You could get that in a 1-minute exposure. Of course, we have all this stuff around Orion, but Orion's sinking down into the horizon by morning. By a month, but also in the morning. Because now I go to the 9th at 5:30 in the morning. Here's Leo here, Virgo is now in the southwest, so they've moved across the sky all night. So tomorrow morning, when you get up, you're starting to see the parts of the summer Milky Way coming up. So the Milky Way is actually a big scoop like this in this diagram. So this arm has sunk below the horizon, and this arm is coming up. And it's because the galaxy is tilted with our plane, so as we go through the night, you sort of see it changing its tilt like that as the Earth rotates toward the other side. This part of the Milky Way has all of the goodies in it, but you know, you could wait till September to explore those and be an awful lot warmer. And so usually, if you're up that long at night, we'll spend some time looking at the stuff in Cygnus here, but probably anything lower than that, unless it's exceptionally warm and clear night, you probably wouldn't want to spend your time there. The one thing about the sky, if it's not good now, it'll always get better a little later on. We get into taking a look at the evening, the horizon tomorrow, take a look at this planet. Mercury is there, just touching above the horizon, too low down to really see. So we have Mars and Uranus that are higher up. And the moon is now, doesn't show very well here, but a very, very thin crescent moon tomorrow. You can find Uranus quite easily in a telescope or binoculars, but it doesn't really look like much unless you look at it through a telescope. And even then, it doesn't look like much. It's a blue dot, or kind of a dreamy blue dot. It's an interesting planet to photograph through a telescope, because a 1-minute exposure will show you some of the moons on that. So if you get a chance to go out to Glenley, plug a telescope on the club's meet out there, then you'll find that you can get a picture of Uranus and Neptune and their moons, and maybe even Mars if you do it right, with about a 1-minute exposure. So here we are looking in the morning sky now, and we start to see a few more planets. You'll notice a lot more spread out here. So we have Jupiter up in here and Saturn in here. And we're starting to see Neptune coming up over the horizon in here. Pluto is here, depending on what you consider, what you accept from the Kubas. So these are nicely spread out, but it gets a little better when you go up toward the end of the month. And now you see the planets spread out quite nicely with the moon in there. And Mercury has now gone behind the sun and come out on the other side. And it's actually very close to Neptune. So you go 1, 2, 3, 4, 5 planets, Pluto and the moon, all in the morning sky. But if you look, here's the ecliptic, and you see how low this is in the sky. It doesn't come up really high like it will in the summer. And so all of these planets are going to be low down in the sky. Also, certainly easy enough to see. Jupiter is very bright, and Venus is very bright. So they can lead you into finding the other planets with your binoculars. A quick summary of where the planets are. Mercury is behind the sun, or is moving behind the sun right now. And we'll get out in the morning sky in April. Venus, we just saw where that is. Mars is in retrograde motion, which means that it's moving backwards in its orbit, or apparently backwards, because the Earth is passing it. And so, like cars passing on the highway, if you're on the inside lane passing somebody beside you and going faster than they appear to be going behind you. So what that means is that Mars stays pretty much in the same place in the sky. It doesn't sink in toward the sun until it completes its retrograde motion, which it does every time the Earth passes it. And Jupiter is also actually going into retrograde motion when we get into April, but that planet's so far away, the amount of backwards motion is pretty small. Saturn is coming up at 4:30, and by the time you get into next month, it's an hour earlier than that. And Jupiter is at 3 tonight and 1 when you get into next month. So Neptune's coming out from behind the sun in April, and Uranus is, as you saw, up there by Mars in the evening. March 20th, 21 is when you presumably have the best chance of seeing the zodiacal light, because then the ecliptic, where the planets are, stands highest in the sky as we cross over from the sun crosses from the southern to the northern hemisphere. So we've talked about that just about every meeting, and it's the zodiacal light is a glow in the sky that resembles the Milky Way in the very dark sky, and it's actually the reflection of sunlight off of particles and dust that's in the same orbit as the Earth is. It's in the plane of our orbit. Because of the way things are aligned, the sun shining in front of you, but below the horizon, reflects off of this dust and toward you, and so you see it as a cone of light. It's quite easy to see once you've had it pointed out to you, but it's pretty hard to find on your own unless you've got some very nice skies. We have Venus and Neptune conjunction. There's a picture of it here. Again, this would, because Neptune's down around the 8th magnitude, you're going to want a telescope to see that, but they're going to be pretty close together. Mercury at this time of day is probably bright in the twilight. You will also get a conjunction of Neptune and Mercury on April the 2nd as the Mercury moves up toward Neptune, but that's going to be just shortly before sunrise. And we have a couple of conjunctions with the moon as well, particularly Saturn. Of course, the moon is following a track more or less down this way along, at least within 5 degrees of the ecliptic here. So every month it passes these planets one by one. There are several planets that it's actually occulting, Saturn in particular, but it's not visible from our latitude. They're visible down in the bottom end of South America. Daylight saving time starts on Sunday. The sun crosses the equator just before 5 o'clock on the 20th. We have something like the 6th supermoon in a row. believe this is the last one, so we have to go 6 more non-super moons before we get 6 more super moons. And you can see it's not a very unique event anymore. Although I did see some of these things are hard to get going, so I expect there'll be a near supermoon or a quasi-supermoon or something like that when we get to next month. Because I just noticed that the 2024 eclipse across the United States, Canada, Greenland, and Russia is now the Great American Solar Eclipse of 2024. So we're going to have the Great American Full Moon and the Great American New Moon, and now we have an eclipse that goes over half of the rest of the world is the Great American Eclipse all over again. I've been giving them a lot of flack on that on the solar eclipse message board, but they're not catching on yet. Because it crosses America, it isn't great, it isn't American. Anyway, new moon on the 5th. This is important because it's Messier Marathon time. And what do you do in a Messier Marathon? Well, Charles Messier was a comet hunter back in the 1700s, and he kept running across all these fuzzy things in the sky. It confused him, and he thought they were comets, so he made a list of all of the things that he didn't want to look at. And so today that list of 110 things is all the stuff that we want to look at. He discovered a lot of comets, but he's famous for the non-comets that he discovered. So there's 110 of them, and it turns out that in April, but March and April, you can see all 110 of them in one night, providing you don't live in Winnipeg. You can only see about 108 of them, or 107 in Winnipeg. So you have to be a little farther south to see all of them. So April is Messier Marathon month. So you just stay up all night, and you go after them, one after the other. Who's done that? Did anybody? Jerry, have you done that?
Nope.
Stan's done it. How many did you get, Stan?
Me? 106.
106.
But I was with Sean on that night, and he got 107.
Okay.
And he did his with no charts.
There you go. Been done. If you see all 110 of them, you can get a pin from the RASC because in addition to the beginner certificate and the sky list that you have to watch, you can also get one for Messier objects or NGC objects, which is another catalog, and so on and so forth. So,
Jay,
new moon weekend.
can I mention one thing about that new moon?
Sure.
On April the 5th, the new moon's really early in the morning, so in the evening, we have an opportunity to go looking for it. It's about a 17 or 18-hour-old moon. So for those who are interested in super young crescent moons, under 24 hours old, April 5th is the day to do it. It's
Yeah, that's another one of the competitions we have is who can see the youngest moon. I think the records, except for the ones that saw it right at new moon, but the record visually is probably about 8 hours or something, or maybe more. But it's pretty close to. It helps if you can stand on a mountain with really clear skies in the direction of the moon, and Juba Mountain doesn't count. Comet Iwamoto was still around with us. You might have seen a picture that Gail sent out, or Sheila sent out not very long ago. But I think I put it in Winnipeg when I sent it out to you. It's getting fainter, magnitude 8, which is still within binocular limits. But it's now past its peak brightness and it's coming down. It's actually quite nicely placed. This is the constellation Orion here. And it's moving very, very slowly in toward here. So even in a month, it's only gone about this far. So you can sort of look at the bow of Orion here, or the shield, or whatever, the hide that he's holding there out in front of him. And just be looking in this area for another little while, you'll be able to see the comet, especially if you have a telescope. You can see the brightness comes down, or the predicted brightness comes down pretty quickly on that. So with this kind of decline in brightness, it's probably with us for only another, the rest of this month. And then down under 10th magnitude, nobody looks at 10th magnitude comet. Not in the winter. The from the picture that Sheila sent out, it looks like it's lost its tail, or at least in the exposures that she had done. And I'm going to finish up with some telescope mirror cleaning tips here. Thank you very much.
Everyone hear me? Let's put this. Is this the right pointer?
It is.
Okay, so there's actually a lot of new stuff out there, but I figured what I'll do is just sort of start close by Earth and just head out into space. So first off, there's actually a contest to name the 5 new Jove moons that were discovered. Actually, it was interesting, but I don't have a Twitter account, so I guess I'm ruled out. And then, as you start to read the rules, it gets tricky unless you're really good with basically Jupiter or Zeus, the Greek gods. It should be about a max of 16 characters. And if it's going prograde, it has to end with an E, and retrograde, it has to end with an A. So, unless you're an expert in Greek or Roman mythology, good luck. But yeah, I think it's pretty cool. Like, there's a lot of rocks going around Jupiter. So, and the contest date ends April 15th. So this is how they do the tweet here. 280 characters. Okay, so you may have noticed. I don't even did that picture work. Okay, it did. So you may have noticed that. Could anyone guess what that was? I don't know if I can.
You're talking about the mirror.
Yeah, there was. Oh, there we go. Hang on. Oh, too late. Yeah.
There it is.
Yeah, so, yeah, I've been sort of tracking the downloads from Ultima 2. Turns out, it's not completely round like a snowman. So basically, I guess as they're approaching it, they saw the face of it. And then as they were leaving, they took several pictures and they put it together in a movie, and they figured out that it's actually kind of flat. So, I guess that's it for the snowman jokes. Really crude drawing. So, right. So I thought I'd talk a bit about, just mention, add a bit of notes on how they discovered it, because basically New Horizons had left around 2006, and meantime they were searching for the next thing to find that's close by. So Hubble discovered it and discovered something in a Kuiper belt object in 2014. And it was actually, they were trying to, after they discovered where it was, they were trying to do some occultation of it to determine if there's any debris around it, so that they could adjust the course for New Horizons so it would run into any debris. And it's actually quite an interesting story. You can read it in Wikipedia. There's a lot of cloudy days every time they go out to view the occultation. And there's an entire NOVA episode on it also. But in the end, they did manage to, in 2017, they managed to get it from 24 different vantage points
by observing this waking out from the 20 different vantage points, they actually kind of knew what the shape was before. They figured it either was a contact binary or two separate objects. I think it was a third option too, so I just thought that was interesting. Speaking of which, you too can discover Kuiper Belt objects. Turns out, these people in Japan, on a shoestring budget, discovered yet one of the smallest Kuiper Belt objects, 1.3 kilometers across, and ultimately is roughly on average 17 kilometers thick by 32 kilometers long. And this object is 52 astronomical units out, and if you don't know what that is, that's the distance from the sun to the Earth. That's 1 astronomical unit, so it's just a measure. It's a good way of thinking of how far things are out. So, so if you have a bit of cash, you need about 228 centimeter telescopes, off-the-shelf CMOS cameras. 60 hours in observing 2,000 stars, and you might get lucky. On your own. So it's actually quite interesting. So basically, they were trying to show that just everyday person can still do this. Can also do this.
They did 2 observing sessions, and there were 30,000 images they had to search.
And I thought this was interesting. Is there Planet 9? Because you hear this come up all the time.
No.
And in fact, I believe there's a How the Universe Works episode on it. I actually like those shows. They're quite good. And so they did some more studies and calculations and whatnot. And you can see here on this diagram, these purple lines are the ones that they suspect are influenced by Planet 9. The green lines, or these orbits, are the ones that they know are influenced by Neptune, and there's the red inner circle is Neptune. The yellow circle represents the mysterious Planet 9. And basically what they did was they checked all the information, did a lot of calculations and simulations, and they said there's a 1 in 500 chance that this is a cluster that it's and not due to Planet 9. So it's by saying that it's not a cluster 1 in 500, then it's highly likely that there is a Planet 9. And the planet is expected to be around 5 to 10 Earth masses. So this is just a diagram. There's a planet Earth. And this is called a super Earth. And a lot of sun-like stars that they search for planets around, they see these super planets. So if we ever find it and go out there, we'll have some, at least a model or playground for understanding other systems. And I found another interesting article, how much does the Milky Way weigh? And the latest measurements now it weighs about 1.5 trillion suns. That's the mass. But and it has 2 billion stars, and you think, oh, that's amazing. And then you realize that 95% of that mass is actually dark matter, stuff that we can't see. And we know it's there because if it wasn't there, from all the measurements we have, we know that these stars would just fly off, like our galaxy would just fly apart. So we know there's this dark matter halo. And all these little spots here are globular clusters, so little, you can see them in Cassiopeia and stuff, they're just clusters of stars, and they're orbiting around our galaxy. So they took 34 from the GEO survey and 12 from the Hubble survey, and they carefully watched these. They could actually, some of these, they can measure how fast they're moving. And from all those measurements, they can tell the mass of our galaxy. So if it's very heavy, they'd be moving more quickly. If it's lighter, they'd be moving less quickly. So that's how they determine the mass. So I thought that was interesting. And then lastly, this is some spectacular image captured by Hubble telescope, and it's NGC 652, which is now A and B, because it's resolved that there's actually a collision taking place. And over here is sort of a simulation. I managed to get this from the website, the the actual survey website. There is one on YouTube where they show this, and then they freeze it, and then they show a picture that's similar to each phase of this. So basically you have two galaxies, and they're basically colliding. So for instance, Andromeda galaxy, this could be Andromeda comes through. And so what you have is, you can see this dance that they're doing, and eventually you sort of get this elliptical type galaxy in the middle. But what's interesting is, well, you can't actually watch this in your lifetime. You've got to be a long PhD, right? So what they do is they model this, and then they look for examples that are frozen in time at each different phase of a collision. And there's many, many examples of this, so that gives us a sense of that we're doing the right calculations.
Michelle, I have
Yes.
a question for you on this. So some of these interacting galaxies, like I noticed on the diagram, they were showing it's spitting out a whole bunch of suns. Are there some of these, just call them intergalactic rogue stars, generated by these kind of interactions? Because at some point, it just looked like it was spitting out a whole bunch of stars, almost like spraying water out in the, you know what I mean? Is that a possibility, that there's a bunch of stars that we can't, that used to be present in one of the other galaxies, that just all of a sudden is like, almost like getting a hold of them?
Well, I would have to say in general, yes, that's possible. It really depends on the environment, because there could be something else nearby that causes a mass that causes them to strip out. But in general, if you have an isolated system and it's doing all this dynamically, it can't fly apart. It can elongate or do whatever. So it's like an ice skater. If you're spinning like this, you're spinning slowly, you bring your arms in, you spin faster. So all those, my arms represent all the stars in that system. So you can see how these are dancing and they're coming back and forth and they're doing this.
But you have two quarters and it almost looks, just from the, I mean, obviously you can't see further back and they haven't run it the full extent, but I'm just wondering if a few of these stars might borrow anchor.
Yeah, no, the answer is yes, I would imagine so.
Gravitational assist, right?
Yeah, I'm sure some will be tossed right out of that interaction. The end result is that then we lose some rotation in the system. So, in general, I would imagine there would be rogue stars. But I don't really know if people have seen them. Maybe we have. We don't want it in the news. Any other questions? That's my last slide. So.
Pretty nice job.
Michelle, that's excellent. All right, we're kind of like usual, earlier than usual, so we'll take our break now. We'll resume at 9 p.m. So I'm going to stay up here, and I think a few other council will probably stay up here. If you have any questions, as I mentioned before, the mentor program or Glenn Lee or anything of that nature, we'll be up here to answer your questions. Okay, again, we'll resume at 9 o'clock. Thank you. All right, thank you. Okay, Conrad?
Okay, greetings. Can you hear me okay? Yes. Really well, or just so-so?
So.
A little louder.
Okay, I'll speak a little louder.
There you go.
Maybe just speak closer. Okay. Good. Okay, well, I'm pleased to be here. I worked with Star Tools for 3-4 years, and I just love some of the results that I can get out of it. Maybe before I start there, I thought you guys should introduce myself. I don't show up at too many meetings. I've been to a few observings, etc. But my My name is Richard Conrad. I'm a musician, classical musician by trade. I play piano, I teach, and astronomy is something that I've always been fascinated with. Might have been a lull at some point, but then I had my second child who started to ask about the planets. It's just kind of caught on fire again. I started off as a visual astronomer. In fact, I still have a telescope. But I got a little ambitious, and I saw a really good deal on, I think it's Astromart, for a 20-inch dog. So that's one of those 8.5-foot high instruments. And I was advised, start off small. But no, I went and I did it. And the amount of effort to try and pollinate the thing, transport it, ended up breaking the mirror slightly. Anyway, I sold my telescope. Jerry?
Yep.
Hey, Jerry.
I'm working on it.
Because that is one comment my wife made to me when we were going out. I boasted about my 20-inch mirror, my 20-inch dog, and she said, I want to see it, and that just never worked out. So at some point we'll become busy with you. That's all right.
We'll work it.
Okay. So I don't get out very much. I have some data on my own, which I process through Star Tools, but because I get out so infrequently, I spend most of my time processing others, and there's quite a bit available that you can get at. Astrobit is a great site. It has lots of raw images. I belong to the Yahoo DSLR processing group, and they submit a monthly challenge. So anyway, I thought I would just start off by showing you a quick slideshow of just some of the images I processed with Star Tools. Hopefully the quality is as good as the screen here. Okay, and I'm going to apologize right away to say I don't know or can acknowledge everybody's data. I know I should be doing that. Scott Rosen is his data. That is Jim Misty. It's Eric Coles. Cave Nebula. M24, I think. And that's the Dark Shark. That's data by Scott Rosen. The Heart Nebula. And that's Jim Misty's M101. Blair McDonald's, he called it Urban M81. Jim Misty's M51. Mark Lundell's Veil, that's bicolor. These are all bicolor, so it's using just hydrogen and oxygen 3. Crescent Nebula, again just hydrogen, oxygen 3. And Tadpole. And these are Hubble shots of the rosette. Elephant Trunks Nebula, again Hubble. And that's part of the wall, the North American nebula. Sol. And that's M8. Oops, sorry. That's mine. That's my first photo. This is Wells, the Andromeda Galaxy. That's one of my first photos in a different processing of it. So anyway, that's just some examples. Gotta shut this down. anyway, before I sit down and sort of process in front of you, just maybe a little introduction about the program. Okay, Star Tools is rather different than other software. Now, I have to say that I'm not that experienced with other software, but just from what I've heard, for instance, there's no histogram. So there's no sort of, I know when you stretch an image, you want to keep the light from getting clipped, so you're watching a histogram. But there's no histogram in Star Tools, and there's no actual manual stretching of curves. Okay, the developer quotes histogram transformation curves are considered obsolete. Here, image analysis is used to achieve results in a more intuitive way. And I'll show you what I mean by that as I process. But there's a certain automation, there's a certain almost intelligence that's working through this as it analyzes your data. And in some ways, it just seems to be doing it itself. Of course, you have all the controls. Okay. Probably one of the most unique features of Star Tools is its noise reduction handling. Okay, and Ivo Jaeger, the developer, calls this tracking. Okay, so the idea is that from the very first stage, all the way through processing, Star Tools is tracking where your noise is. And in astrophotography, noise is the big demon. It's always there. It's always trying to cloud the signal, etc. So I think this is significant. So in other words, keep keeping track of your noise all the way through. So when you finally actually denoise your image and get rid of that, you're also you're leaving as much detail back there as possible. Okay. So, well, you've had a chance to read that. The pros, it's only $60 or so. At least that's what I paid for it a few years ago, but it would be the equivalent in euro. Images process rather quickly, intuitive interface. As I said, excellent noise reduction algorithm. Okay, efficient analysis of dynamic range, bringing out details. And then you also get one-on-one with the developer. And this is maybe a little unusual that we think of all the big companies, the Photoshop, etc. Whereas this is kind of a one-man thing. And he's got another job. This, I think, was just a hobby. And now he's doing his real job. But on the side, he's heading a forum, and he's answering people's questions in a fairly timely manner. So, so that's good, as long as you're still with us. In the cons, it requires a fairly fast processor on your computer. You can do it with a slower computer for sure, but you have to reduce the resolution a little bit to get that. But as I'll describe during the processing, that actually reducing resolution actually increases detail in some ways. Okay, the forum is good, rather small. Okay, and some elements of the program are somewhat crude. For instance, when you're going through when you're going through the process of tracking to the point where you denoise, you basically have to go all the way to the end, then save. You can't quit in the middle. So anyway, this along with a few other suggestions at the forum, he said he's working on. Okay, yeah, I'm going to maybe dispense with this. I think I'd like to show you how it works. Okay, well, right here, it says auto dev. You're going to auto process your image. You're going to crop the artifacts, wipe the gradient, re-stretch it, and at the very, very end, you're going to add your color. But in Star Tools, in fact, is working in the luminance channel only. So you'll be seeing some color as I process, but that color is not really allocated and is not being processed. So I think I'll just go ahead and start.
On the right.
Okay. There we go. The star. Okay. So I had a bit of the decision-making situation going on. I wanted to show you as much as I could in the short time that I have. And so I thought, well, why not show you some kind of average data or data that we would normally get ourselves, rather than show you that that's the best amazing data. But what I thought I'd do is I would just start off a few steps with this M42, okay, which is fairly average, and very quickly move on to something else. So I wanted to show you something. The first step we do is auto depth, okay? And what this does is it stretches your image out, like right to the max, okay? And the purpose of that is basically to show what's going on, what's going wrong with the image. Okay, and as you can see here, there's a whole bunch of not just gradients, but I don't know, there's vignetting. So this could be due to improper flats. It could be due to light pollution or both. Okay, so, well, I'm going to keep that. Okay, but we want to get rid of those. So the next tool we use is white. And this would be Photoshop's, say, Gradient Exterminator, or whatever other tool you use to wipe gradients. So, if I leave those obvious things that do not belong to the image, if I leave them there, I will end up with this, okay? Because the software thinks it's real data, okay? It thinks it's supposed to be in there, okay, which we know it's not. Okay, so what we do is we go to mask. Okay, so what we're going to do is we're going to actually crop that. Okay, so crop it in a way that we have none of those anomalies, things that don't belong in the image there. Okay, so I'm going to do something like that. That's probably all that's recoverable. Okay, and I'm going to try that again. I'm going to try to remove gradient. We have a temporary, called temporary auto dip, so we're going to do a momentary stretch on it. Okay, and I'm going to also increase what's called the dark anomaly filter. Okay, because there are likely other things in this image that are not really supposed to be there. It could be this looks like maybe a dust donut or something on the sensor, and there may be other things going on. So to be on the safe side, we're going to get that to 3 or 4. So that's basically going to try and ignore that information. Okay, so that did a fairly good job. This is by no means a perfect image, but you can see that everything seems to be fairly even. You don't see any gradients. Okay. Okay, so that's all I want to do with this image. I'm sorry if you were looking forward to seeing how this turns out, but it's probably going to take too long. Like I say, it's the better the data, the less processing you have to do, just so for this time frame. But let's just say that, you know, you really like the software you're working with, but however, you like the white function of Star Tools. So what you can do from here, you're going to keep it. And you're going to restore it now back to its linear state. Okay? That was the original one, only linear white. So now you have an image that you can work on with other software that has been, where the gradients have been eliminated and have been cropped properly. Okay, and then you just save that. So what I'd like to process for you instead is Jim Misty's M31. Jim Misty has put quite a few of his, a lot of his data online available to use. He's got an enormous telescope in an observatory. Okay, so type of data, linear, was Bayard. In fact, this comes from a CCD camera, which I put together. So this would be the option that you would say. So when you stack the individual frames together, you have to make sure not to choose white balance. That's very important. This Star Tools really likes to work with virgin data. Okay. So I'm going to, the first thing is the auto deck. Okay, and so the colors are here. Just because this is green really means nothing. It's just the way it looks, but color will be calibrated further into the processing. Okay, so we have some stacking artifacts here, and so it's quite important to crop that out.
Did you already stack this on Star Tools?
This came already stacked.
Okay.
Yeah. Yeah, some people supply their data, like all the files, right, and you stack them, but that's just a lot of work. So, okay, so keep this. This is full resolution, and so this is taking a little bit long. As you can see, there are moments of silence here. But later on, I'm going to reduce the resolution a little bit. You're going to find that you can work with images like that a lot easier. Okay, so I'm going to also rotate this to the perspective that I like. So 180 degrees. Keep. So that's my personal preference with the Andromeda Galaxy. Okay, and this is pretty clean. There's not a lot of wiping that needs to be done, but there's a color cast, so I'm going to hit wipe. Again, these stages at the beginning, it's very important to follow them. That's part of a very standard workflow.
Does Star Tools stack pictures?
No. No, it doesn't.
Do the various steps come in a set of instructions of some sort?
Yeah, the website. I didn't end up describing some of the functions. I'm sorry. You'll have to see it while I'm doing this, but I was going to talk about that a little bit. You can see that on the website, and there are a number of videos too. So, okay, so this is a temporary stretch that's showing you what it would look like at a certain stretch, and it looks like the gradient's pretty good. So we keep that. Okay, so now that I have a fairly clean image, okay, I'm going to re-stretch it, and this will be for the final time. And this is probably one of the most important steps I find, because this is how it works. Instead of adjusting curves, you simply drag your mouse over a region of the image. Okay, so say like that. Okay, so that's what we get if we do this. Or you can do this. But I have to be honest that with images or galaxies that are aligned this way, it's actually a little tricky to get sort of the right slice. You know, that's not bad. So what I'm going to do, and this is just a little bit beyond basic, but it's not complicated. So what I'm going to do is I'm going to orient the galaxy so it's completely horizontal. So I go to rotate. I'm just going to move it so it's easier to sort of select as much of that as I can. Okay? It's not going to stay like that. It's just for the purpose of the selecting it for the auto dip. Okay, so this is amazing data. I've never seen, it's got the halo around it and everything. And so I want to show that. So I'm going to stretch something like that. It may take a few tries just to get what you like, but it's quite important. It saves you some time throughout other processing steps. Sorry.
What forms of files does it accept?
TIFF and FIT.
Not raw, Canon raw?
It has to be converted to, well, when you stack an image,
Yeah.
it becomes a TIFF or FIT. Yeah. So what? Okay, so we'll work with what we've got here now. Okay, so I'm going to keep that. And this is just a little bit tedious, but I'm just saying for galaxies like this to really get a good... and so what I've done is I've tried to optimize the dynamic range within this. So it'll involve just a little less contrast, maybe just a little less sharpening, etc. Okay, and if one didn't like this sort of halo around M31, then you could work at it differently. Okay, so I'm going to reposition it. Okay, and once I've done this, it's very important now to crop again, otherwise I'm just going to get all this black area. Okay, so the next step I'm going to take here, it just seems, it might seem crazy, but I'm I'm going to reduce the resolution. Okay, one would say, why throw away all that detail, all the resolution? But the fact is, cameras have way more resolution than you need for subjects of any kind, really. Excepting perhaps if you want to resolve the very, very smallest star. But this will also do. I'm going to bin this down to, this is 200%, so I'm reducing it. I'm reducing this by half the resolution. And I'd like to do more so, but the problem is the stars would end up, the smallest stars would end up looking like squares. Okay, and now this is a further step, and this is just personal. I mentioned that Star Tools works within the luminance channel, the black and white channel, but there still is color in that, and I find it distracting when gauging contrast and stuff. So I'm just going to, I'm in the color module now, I'm just basically desaturating it so there's no color at all. And that's a personal preference, but the developer has said that that's just fine, that won't harm anything. Okay, so I think the first step I want to do, we have a very intense galaxy core here, which some may like to smooth that out. I'm going to do, sorry, I'm not showing you everything. I'm going to go into the HDR model, okay, module, and I'm going to hit equalize, and that basically makes the brightest objects dimmer and the dimmer objects brighter. Okay, not a lot, but just a little bit to see if we can brighten the ends a little bit more. So this is all my personal preference, of course. You may not like what I'm doing, but I'm just showing you how to do it. Okay, before, I kind of like that. Okay, within the HDR module, again, they have an algorithm called reveal, okay, which will actually go to the brightest parts of the image. It says reveal deep sky object core, and that's referring to the core of the galaxy. What it does is it brings out contrast within the brightest areas. So I'll show you what happens. I'll set it fairly aggressively so you can really see what that does. Oh, it's hard to do anything, sorry. That. Okay, so you see what that's done. Okay, so that's quite amazing in a way, the detail that you can't see that suddenly is there. But look what's done here. And I think the core is just slightly overexposed, and so that we have to deal with that too. So I'm going to reduce this a little bit, because I'm going to do some more sharpening on top of that. I don't want that to become overdone. So I'm just going to start basically to bring out the detail, just slightly, so I can tease it out using the sharpening tools. So I'm going to leave, that's pretty good. Okay, so my preference now, what I would do is I would go into the contrast module and bring out some details, again, in the brightest areas. So there is a dark anomaly filter, which you saw before, and I'm going to set that a little bit higher because I don't want to sharpen. I don't want to the contrast to consider the noise gradings at all. So I'm going to set it there. And I'm just going to show you what it can do. So I'm going to actually set the aggressiveness a little high. Okay, so you see what that has done. That's quite nice if you like it to be bright. So that's overdone as far as I'm concerned. Try somewhere there. that's more like it. So I'm going to take a second pass with the contrast module. And this time I'm going to set the compensate gamma for yes. And what this does is it applies the contrast as before, but then it also compensates by giving a slight stretch. So what this looks like is really more of a localized or very fine, it's a finer, more aggressive kind of contrast. You'll see that in a minute. Excuse me, this part usually takes a little bit of experimentation. One last time, I promise. Okay, we're just going to make that work no matter what. And yeah, that actually looks fairly decent. The dark anomaly headroom is a little difficult to explain. When the gamma is set to no, as I understand it, the pixels that you have chosen to reject are put near the top of the histogram if the dark anomaly headroom's gone to the right. If it's gone to the left, it goes to the bottom. So it has a way of actually breaking the background a little bit, and this way darkening. It doesn't work that way with the compensate gamma, sorry. Sorry, I can't explain it. Okay. Okay, so I've done pretty much what I can do as far as the contrast goes. So what you're looking at is a little bit lighter than what I'm looking at on my screen. So that's how that translation goes. So I'm going to now sharpen it. And fairly integral is knowledge of how to use the mask and star tools. So what I'm going to do is I'm going to highlight the galaxy with the default brush mode, flood fill, light the pixels. So you start in the dark end, and it will flood fill the pixels as they get brighter. Okay? Throw that. Keep it. So yes, anything that's green is going to, I'll be able to apply the sharpness to. But I don't want to sharpen the stars. So I go back to mask. Auto. I'm going to choose fat stars. And I'm going to select old mask, subtract. So I'm subtracting the stars out of the green, out of the mask, so that they are not sharpened. Okay, so I'm going to invert that, see what that looks like. Okay, that's pretty good. I'm going to want to grow that a little bit. One more. That's too much. Okay. So I've inverted the mask now, right? So it's doing the opposite. But here's a chance to look for things like this. There's a glow, kind of a major glow that has to be covered. It has to be covered because when you sharpen, it'll be quite apparent. So, but I think it's pretty good. So I'm going to sharpen now. By default, it's set for large scale sharpening. So large scale sharpening just simply means that it's going to give a good general sense of contrast without too much superfine detail. So that's pretty much what we want for this. I think we just want this to really stand out and see what's happening there. Okay. And here you have 5 sliders, and you can adjust these. This is the smallest scale of the large scale. Okay. It's set for mask fuzz, 8 pixels. That means that it'll bite into the star a little bit, but I think this is too much. Something like that. And I'm also going to bump this quite a ways. Just about experimentation. Okay, so that's made quite a difference.
Nice.
We will try a wee bit. Okay, so we can also go into medium scale sharpening. Okay, so large, medium. Okay, and my timing is, I've discovered, at least my opinion, is that this is overlapping with large scale. So I removed scale 5, but that, of course, is anybody's choice. So you can see some of the detail that we drew out with the reveal core. That's coming out better now that we've sharpened it. And it may not have been there much at all had we not done that. I'm not doing that. Okay, so we'll settle for that. Okay, another tool of Star Tools, going to clear that, it's called deconvolution. And what it does, basically, I'm going to choose, ask it to generate a mask automatically, and it makes a star mask. So basically, it's going to mask everything but the stars. So the deconvolution is going to go under the image, but probably more importantly, it's going to go around the edges of the stars. Okay, and so what it's doing is cutting down the haze. It's actually sharpening the stars. At the same time, it's going to sharpen the image slightly. The deconvolution tool is used to improve images that are used during poor seeing or bad transparency. So let's see if it's done what it's done. You can see right away that it's sharpened the stars a little bit, kind of removed the fuzzy edges. So I just like to bump that up. So I bump up the radius. It's basically going to be biting down on the star a little bit more. And it also increases the effect of the deconvolution underneath. So we can do that until the stars just don't look very good. Okay. Probably a little much. And apply that to all. By the way, I didn't say, I've sped down, sorry, I've done this so that it sort of reveals itself to you a lot quicker, so you can see the result. Okay. Now I'm going to say all, and now it's going to apply that to the entire image. Please feel free to stop me. I've heard some people ask questions, but I'm happy to pause for a moment. So many images, starting at full resolution, can be binned down to 4 times their resolution without any loss of detail. And that, of course, will speed the computing time greatly. Okay, so we have that. And there are a lot more tools to use here, but I think that's all that this requires. So what I'm going to do is I'm going to now add color. And there are basically 3 ways to do this. One is simply just to click color and let it find itself. I find, yeah, this image, you'll see there's a lot of green in here. And if we click max RGB, we'll get sort of a map of what's going on, which is kind of cool. It means that you can even do this, say, on a computer where the monitor is calibrated perfectly. And you can see that there's more colors to see. And in the galaxy, we should have red and green and blue all around. So I'm not sure why. One reason is that it's picking up the noise, and so it's not doing it properly. The second way, and this is a preferable way, is to select all the stars. Okay, and once you've selected the stars, the total sum color of all stars is white, and so that gives you your color balance. But for some reason, the data of this image, I'm not sure how it was stacked, but that doesn't work well either. So what I've done, get my color, is I've simply highlighted the galaxy itself, where the brighter parts of the galaxy is ideal. Since the stars were a problem, I'm going to subtract those. Subtract. Okay, so now under color, I'm going to keep the mask. Okay. I'm going to sample this area to get a proper white balance. Okay, and then I'm going to go to the mask. I'm going to clear it. Invert it by applying that information over the entire image. And keep it. And that should work fairly well. And so we can check our colors, just in case. And we have a proportion of green and red and mainly blue. So I think that's fairly close. You can also play around a little bit here. Cap green, that basically tells it to avoid as much as possible reading the noise, which gives it a greenish tinge. It may or may not make an effect here, eh? But I'm just going to bump the green down a slight bit. Okay, and then of course this is what is supposed to be scientific color. This is supposed to be accurate. However, from here, the saturation is up to anybody. Dark saturation, I often like to increase that. That shows color more into the ends of the galaxy. And that's obviously just taste. Okay, so let's just say that that's all right.
I can take a little blue out of it. It's a little bit too saturated.
There's more that I could have done, I think, but I would rather you just have a good taste of this and not keep you into the wee hours. and now the last stage is to denoise. Okay? So, as I mentioned, to this point, Star Tools had been keeping track of the noise. So it knows where it is. And so I disengage tracking and start noise reduction. Okay, so it starts off with a blurry screen, and basically what it's trying to do is identify the largest noise grains. So what you want to do is basically blur it to the point where you can't see those noise grains. So let's just reduce the grain size to 0 or to 1. Okay. And this is a pretty incredibly noiseless image, as you can see. There's almost nothing to see. If I went really, really close, you could probably see it. So I'm just going to say the grain size is basically almost super tiny. This wouldn't be average, obviously, unless you had this equipment. Obviously, this image has a lot of acquisition time. Okay, so this amongst a few other of the algorithms takes a little while. Okay. But while this is going on, I could just maybe talk to you about a few of the other tools that we won't get to see. One's called a star sim, which is quite interesting. It actually generates a physically correct diffraction and diffusion of starlight based on a virtual telescope model. So in other words, you can kind of choose your telescope, and it'll generate the stars that telescope would give you. So it sounds pretty synthetic, but in some cases where you just have bad luck with your stars, or if your telescope or lens just doesn't do well with stars, you can actually use that to improve them.
Mm-hmm.
It's kind of neat. Okay, so obviously there's not a lot to do here, but let's just zoom in a bit. There we see a little bit. Highlight that area like we did with the deconvolution. And see if that makes a difference. Yep, so a little bit. Okay, so we're just going to do
Get a noisy image.
full, and that's going to take care of that. So to continue this, once this is done, there are other things you can do. I've made an image of this where I've actually removed the stars and worked on them. I think one of the versions I made had a bigger halo. So when I removed the stars, you can see the halo a lot clearer. So you can do that with Star Tools, but obviously I won't have time today to show you. But I wanted to show you one more thing. Okay, so now we've done the tracking process, because I've denoised, and now a lot of the other modules are now available to me if I want. It has see the things I haven't used. It has a lens module, which will take it into consideration if the image is needed a field flattener or something like that. It'll actually correct it. Okay.
Distortions from where
Banding. If banding is an issue, horizontal or vertical lines, this module will take care of that. Anyway, so let me start maybe with something I haven't described called the life module. Okay, so I'll try to explain this the best I can. That a certain amount of light is lost through refraction, and also through various processing stages, we lose some of that light. And Star Tools light module tries to remodel this and attempt to restore sort of a natural glow that's supposed to be there. That's the best I can explain that if you want to ask questions later. Anyway, so it's by default it's set for glow threshold 12. I'm just going to do that. And the detail preservation here is set by default to minimum distance to half unity, which the developer has said is a fancy way of saying gray. So that would mean, I'm assuming that would mean mid-tones, that it focuses on mid-tones. So that's what this has given us. Okay, a little subtle for my taste. We can also choose this glow for maximum contrast. That's there, that's very subtle. Power the inverse, so by reducing the percentage, we increase the strength. Okay, and maybe as a final tool, just to round this off, I'm going to reduce the stars a little bit. So I'm going to go to Mask, Auto, Filter sensitivity, the higher it is, the less sensitive. The lower it is, the more sensitive it will be, so this will attract more stars, less stars, or even bits of the galaxy, which is not what we want. Okay, so we take a little look here, and I'm not going to spend much more time at this, but if I had more time, you can do things here. This is fairly well covered, except for the bigger stars, so what I would do is I would grow blob, if I can cover those stars better, because I want to shrink them. I want to shrink them right from their edge. Okay, but I think you're going to get a general idea here. I'm just going to take this one. Okay, so keep that mask, and now I go to Magic, and here we have a number of options, but here by default it's set for shrink. Shrink 1 pixel. I think that should have already done it. Okay, you see the difference. Okay, so there's more that I could do, but it's Friday night, it's getting late, so thank you for listening to me.
Thank you, Richard. All right, okay, that will conclude the meeting for March. Thanks for coming down. We'll continue on the second part of the discussion. Unfortunately, I wasn't able to make reservations for the one in Pembina. For Boston, we have one on Taylor. So we're going to have to head out there. Apologize.